Hey, this is your worksheet, AP Calculus definition of the derivative practice. And I've gone back and I've rewritten the three different variations that we would see of the limit definition of a derivative. And all three of these can be found on your yellow study sheet. Now, as we go through each problem, it would be a good idea to refer back to one of these three formulas as we work. So let's look at number one. We have the limit as x approaches pi. And notice all of the stuff that we have. If we do a direct substitution, which you should always try with limits, you have cosine of pi plus 1 over pi minus pi. And a lot of times with students trying this, you get 0 in the bottom and stop, but you need to go all the way across. Remember that cosine of pi is -1, so we end up with -1 plus 1 over 0. So we actually have 0 over 0. So there's no way for us to tell. Now don't be tempted to choose that one. That's not necessarily going to be the true case. But if we think about the example we just saw with the limit as x approaches a of f at x minus f at a over x minus a, we see this is just a variation of the limit definition of a derivative. Notice that my f of x is here. Now f at a, well, we have a minus here, but we have a plus sign up here. And our a value in question is pi. But notice that we saw that cosine of pi is -1. So really what I have here is the limit as x approaches a of, let's say, cosine of x minus cosine of pi all over, and let's see, x minus pi. That's really what we had originally, and really we could change that a there. Let's go back and change that to pi, because that's really what's going on here. And notice again, that fits very nice and neatly into that definition of a derivative. So that means I need the derivative right here of cosine, and then we need to substitute pi in for that. So all of this really condenses down to sine. The derivative of cosine is negative sine, and we want it evaluated at pi. So that's going to give us 0. So the correct answer for number 1 should be 0. So hopefully you recognize this. Please don't fall into this trap here of choosing non-existent. All right, moving on to number 2. Number 2 is a little bit more straightforward. We see right here, there's that x plus h pattern. So we really just need to find the derivative of this function here. And we did always move out our derivative, or our exponent, sorry, to the outside. And so that helps us see that we do need the chain rule here. So if we do our chain rule, we have 2 sine 3x, and all that is raised to the first power, times the derivative, again, all that to the first, times the derivative of sine, which is cosine of that angle, times the derivative of the actual angle, which is 3. So notice that's going to be answer choice B. Okay, moving on to the next problem. Again, very similar. We have our x plus h. Here's our minus f of x, so there's our function. So if we can identify that f of x, these problems go by pretty easily. So the derivative of x to the 5th, or f prime, is going to be 5x to the 4th. We need this evaluated at 2. So f prime at 2 is going to be 5 times 2 to the 4th is 16. So that looks like that's going to be 80. So number 3 should have been D. Okay, and let's see, number 4, very similar pattern here. We're really just looking for the derivative of our function here. So we have our power rule. So we're going to do 3/2 times 2x to the, if I subtract 1, I get 1/2. And so let's see, those will cancel. So that's going to give me a 3x to the 1/2 power, when the 1/2 power means square root. So that tells me answer choice E. Okay, number 5. Now number 5 is a little strange. It almost looks like we have a pattern here, but notice that both of these terms here, those are x's. So let's see what happens here. If I go ahead and I plug in, I get sine of 0 over 2 plus 0. That's minus 1 all over 0, which is still looking kind of strange, but the shady part of this, we've got a minus 1 here, and we don't have an h anywhere. So that's really making me wonder about this problem. I think they're trying to trick us. So we have sine of 0 minus 1 all over 0. And so if we continue this problem, sine of 0 is 0. So I really end up with negative 1 over 0. Oh, that's not 0 over 0. And notice I didn't have an x plus h. I had some weird stuff going on with this problem. And sine at 0 is not 1. That would be cosine. So this one, with this being over 0, that tells me that x equals 0 is probably a vertical asymptote here. So that tells me that the correct answer choice here is going to have to be E. We don't have an existing limit there. But that one was kind of strange, and I think they put that in there just to throw y'all off. Okay, now number 6, again, it follows that nice x plus h pattern that the previous problem didn't have. And so I know that my function should be here, but remember it was always minus f at x. And I don't have that here. I have that negative distributed through. So before I start doing any kind of derivatives, I would factor out that negative, and that's going to tell me what that original function is. So 3x to the 4th minus 4x squared plus x. And then we can do the derivative. And so this right here is the actual original function. And so now I can go ahead and say 12x to the 3rd minus 8x plus 1. And so that looks like we're going to get answer choice D. All right, so hopefully y'all got through these first 6, okay? With the exception of number 5, it was quite tricky. Now let's look at number 7. Now number 7, if I go plug in my t at 1, let's see what happens. Well, that's going to give me 1 to the 1,000 minus 1 over 1 minus 1. Well, that's going to be 0 over 0, which is, not sure what that's going to be, because we don't know what 0 over 0 is. Now, we can't treat that like 1 over 0 and say it's non-existent. We don't know that yet. So we're going to have to do t-chart. Nobody likes t-charts, but they sure are useful from time to time. So I'm going to focus on this function right here, and I'm going to plug in some values. Well, I know if I plug in 1, I get crap. So down here at 1, I know I'm not going to get anything. I'm just going to do a dash there. But I want to know maybe some values getting closer to 1, like 0.9, 0.99, and 0.999. And you could even get crazy with it, just crazy stupid, and throw in all kinds of numbers. We could even do point and just throw in a ton of nines there. And so when we start doing that, we get these weird values. And again, I've already plugged in and generated some values for us. So we have something like this going on, and 632, and then 951, and then you keep getting closer and closer and closer. I think you end up with 999. So it looks like from this side, from the left side of 1, we are approaching 1,000. Now if we go to the other side of 1 and we do 1.0001 and 1.001 and just see what some of these crazy values are, and believe it or not, you should get something close to 1,000 over here. So this limit value, as strange as it is, you're actually approaching 1 from each side, and your x values are approaching 1 from each side. But then notice what these y values are approaching. So this answer, this limit value, is 1,000. Now that is so strange, and we really don't want to have to use a t-chart each and every time if we can get around it. So let's go back up here to what we called we have 0 over 0. And this is an indeterminate form because we can't determine a value for it. And if you need a proof of that, just ask me. I'll be happy to go through it with you. But what we can do is called Lhopitals Rule. And L'Hopital is really going to save us some headache because we really don't want to do this plugging in and doing a t-chart for every problem. Now some problems you just have to, you don't have a choice. But with the 0 over 0 situation, we do have a choice. What L'Hopital's rule is going to let us do is evaluate this limit, but we're going to be able to evaluate it by doing the derivative of each individual term. So if I go back up here and I say, well, what's the derivative of t to the 1,000? That's going to be 1,000 t to the 999. Okay, minus, well, the derivative of 1 is 0. Notice I'm not doing any kind of product or quotient rule. I'm just doing the derivative of each individual term. And that's what we can do with L'Hopital's rule. Well, then on the bottom, let's be careful. It's not going to be 0 because we have a t down here. The derivative of t is 1. The derivative of minus 1 is 0. So look at what L'Hopital's rules let us do. It's saying, hey, this limit has the same value as the previous one, but notice the reduced form here. It is just 1,000 t to the 999. Well, if I plug in 1 there, dun-ta-da, I get the same answer. What? That is crazy business right here. Now look at that. So, will L'Hopital's rule work every time? Every time you get 0 over 0. Yes, it will. So congratulations, you've made it to the high five, awesome part of calculus where we can start finding some of these nice little shortcuts to use. All right, so let's see, will L'Hopital's rule work here? Well, very quickly you need to check and see, do you get 0 over 0? Now that's something different. If you get 1 over 0 or something else over 0, then you've got a vertical asymptote. L'Hopital's rule will not apply here. Has to be an indeterminate form. So if I plug in 1, very quickly, 4 minus 4 over 1 minus 1. So yay, hooray, we get to do L'Hopital's rule. So we have the limit as x approaches 1. And let's do the derivative of each term. So that's going to be 20x to the 4th over, and let's see, minus 4, that's going to be 0 over 1. And if I go ahead and evaluate this limit, notice we get 20. And la-ta-da, if we did a t-chart, it would come out to be the same exact thing. How awesome is that? All right, so let's see about the other ones. Let's see with number 9. Again, if we plug in 0, We do get 0 over 0. So let's go and see, can we do Lhopitals rule here? Well, yeah, we have 0 over 0. So, and if it's on a free response, you do have to make this notation here. And then you do have to tell the reader, and you can abbreviate by L''H, that you're doing Lhopitals rule. So we're actually going to evaluate the limit as x approaches 0. And remember that right there is really 4 plus x, all raised to the 1/2 power. So if I derivatize that, so I get 1/2 4 plus x, all raised to the negative 1/2. Now don't forget to do the derivative of the inside, but the derivative of the inside is 1. So if you forgot it here, it's okay, but be careful. Minus derivative of 2 is 0 over derivative of x is 1. So let's see what mess we've made here. So we have the limit as x approaches 0, and that's going to go away. I don't really care about that. Negative exponent means reciprocal of that. So I'm going to have 1 over 2, parentheses, 4 plus x, all raised to the 1/2 power. And now if we evaluate that, well, let's see, if we plug in a 0, I get 1 over, let's see, that's going to be 2 times 4 plus 0, so 4 to the 1/2 power, which is going to be the square root of 4, which is 2. 2 times 2 is 4, so 1/4. Okay, so there's that limit value. And if you did the calculator and plugging in from both sides, hopefully you had it approaching 0.25 from both sides. Should be what you're seeing there. Okay, and now for number 10, you can do Lhopitals rule, or you can really go back to that limit definition of a derivative, because notice here what's going on inside the parentheses. You have 3 plus that x, all raised to the 3rd power. So a couple of ways around doing that. Most people really like jumping on that Lhopitals train, but do make sure again that you know when you plug in, you do get 0 over 0, and then you can jump on Lhopitals train here. And whenever you do your derivative, again, remember that you will need to do the chain rule. So I have the limit as x approaches 0. And then from the first one here, we have 3 times 3 plus x, all squared. And then times the derivative in the inside, but the derivative of 3 is 0 and derivative of x is 1. Minus 0 all over 1. So at the end of the day, when I evaluate this, I get 3 times 3 squared, which is going to be 9 times 3, or 27. Okay, moving on. Number 11, same idea again. If you plug in pi over 4, you do get 0 over 0, which means Lhopitals rule again. So we have the limit as theta approaches pi over 4. Derivative of tangent is going to be secant squared theta times the derivative of the angle, but that's okay. Well, we had x, so oh well, it'll all work out in the wash. So secant theta minus 0 over 1. And so when I evaluate all of that, I get secant of pi over 4 all squared. And some of us still don't know all those trig values. You little turkeys, you need to learn them. So that's going to give me a value of 2. Okay, now let's look at some that's like, okay, now wait a minute here. Cosine of pi plus h. Well, we're still right back to that same idea here. H is approaching 0, and if I plug this in, I get 0 over 0, so we can do Lhopitals rule here. And we know the derivative of cosine is negative sine of the angle. So negative sine of the angle is going to be pi plus h times the derivative inside here, but h and pi are both numbers, so we don't have to worry about that. So what's going to be this limit as h approaches 0? Well, it looks like we're going to get pi plus 0. Well, pi plus 0, that's still pi, and sine of pi is 0. So hopefully y'all got 0 there. Okay, 13. Again, plugging in. We get 2 minus 2 over 1 minus 1. So yes, we're back to 0 over 0 again. So Lhopitals Rule. So we have the limit as t approaches 1 of 3t squared. Oh, y'all, I did not write L'Hopital. I did not make that note there. I would have lost a point here or more, so we got to watch out for that. So our derivative on top, 3t squared plus 1. And then on bottom, that derivative would just be 1. So after we plug in, we end up with 4 over 1, which is 4. Or most days. Depends on what kind of day I'm having. All right, now all of that's great and wonderful, and we're going through saying, yes, Lhopitals Rule this, Lhopitals Rule that, and then we get to absolute value, and it's like, hang on, wait a minute. I don't know how to do the derivative of the absolute value of something. So if I plug in, I get 0 over 0. So that limit may or may not exist. So I need to do some more investigating here. So this is why I did start us out with doing a t-chart. This, you might have to do a t-chart here. So we have x and y, and we're going to look right here at those values. And so h is approaching 0, so let's think about our number line in 0. So we have 1 here and 1 here. Negative 1 over here, goodness. So let's think about this. As we're approaching 0, getting closer and closer, we want really super duper close to 0. So what about on one side of 0? Well, we have negative 0.001. We could do negative 0. And then we could throw in a whole lot more zeros there. And then over on the other side of 0, we could just make that positive, 0.001, 0.0001. And at any rate, but we know here at 0, we're not going to get an answer. But hopefully when we go through and we start plugging in all these values, notice from the left and from the right, as we're approaching that 0, we are going to be approaching the value of 1. So hopefully y'all got that answer. And again, you just have to plug these values into your calculator, and that should generate it for you. Okay, here's another great example of Lhopitals Rule again, because if we want to do a t-chart, sure, but who wants to pick numbers super close to 81? I mean, that's crackhead thinking right there. And if we plug in, we do get 0 over 0. So that means, hey, I've got to employ L'Hopital. And so let's see what we get. We have the limit as x approaches 81, and that's x to the 1/4. So if we do the derivative, it's 1/4 x to the negative 3 over 4. And so let's see what all that's going to encompass here. That means reciprocal, so I'm really looking at the limit as x approaches 81 of 1 over 4x to the positive 3 over 4. And when we plug in an 81, let's see what we get. We have 4 times, that's going to be the 4th root of 81, all to the 3rd power. And let's see, so that's going to be 1 over 4th root of 81 is 3. 3 to the 3rd is 27. 4 times 27 I think it's going to be 108, but y'all double check my math there. Okay. And again, L'Hopital, great way to work out that one. Okay, number 16. Now, number 16, yeah, we could do L'Hopital's rule, but we could also go back to that whole idea that I think this is probably that C plus H. And then right here, that was probably, how in the world could we get a 2 here? Well, if I have a 1/3 here and an 8 here, I bet that's going to be my F at C idea. So I'm thinking that we probably have a function here of x to the 1/3 power. And so let's see, what is 8 to the 1/3 power? Well, it's the cube root of 8, which is 2. So yeah, we probably are talking about x to the 1/3 power. So that's back again to my function. And so f prime of x, that's going to be 1/3 x to the negative 2/3. Well, we need a value to plug in here. And our value that we saw, or that C value, was 8. So we need to say, well, I need f prime at 8, which is really going to be 1/3. And we could go ahead and move that 8 down here. So that's going to be 8 to now the positive 2/3. So that's going to be 1/3 times, well, the third root of 8 is 2, and 2 squared is 4. So it looks like we should have an answer of 1/12. Okay, and again, you can do L'Hopital's rule here, but I take that back. I don't know if I would try L'Hopital's rule here or not. Y'all give it a try and see what you come up with. To me, it might be a little easier to step back a second and look for that pattern. And the same is true with 17. I would step back and look at the pattern for a minute. Notice that 6 is being multiplied both places. H is approaching 0. So in my mind, I'm thinking, well, I know this is wanting a derivative. It's 6. It's going to be 6 times something. I'm not sure what that something is just yet. So I'm going to say, well, I know I've got a 6. And let's see, notice the 1/2 is probably what's being evaluated here. So that I probably need to plug in a 1/2 somewhere. And it looks like the function itself is probably maybe an x raised to the 6th power. And so let's see, well, if this was my function evaluated at 1/2, all that would change over here would be x to a 1/2. So, and that looks like that fits the pattern. So let's do our derivative. So that's going to be 36x to the 5th. And remember, that means we do need to plug in a 1/2. So that's 36 times 1/2 to the 5th. So 1/2 to the 5th is 32. So I have 36 over 32, which is, let's see, I can divide 4 out of both. So 9/8. Okay, and for the last one, again, a good mixture of looking at, hey, I think I see a pattern here. Let's see, I would say my function was cubed. It looks like I have a fraction. It looks almost like a 2 might have been up here. And let's see, looks like we might have had, I'm just going to say maybe an x to the 3rd. Well, let's see, if I plug in 2 right here, that's going to give me 2/8, isn't it? Which is 1/4. Hey, there's my f at c value. It's right there. So my function in question is 2/x cubed. And so I need to rewrite that. That's 2x to the negative 3. And if I do the derivative, that's going to be negative 6x to the negative 4. Now don't forget, we need to evaluate this at, what was the value? Maybe 2. So negative 6 over 2 to the 4th, which is negative 6. 2 to the 4th is 16. And so let's see, negative 3 over 8. So voila. All right, I hope this helps. Please ask me any questions you may have tomorrow. I'll be happy to help.